All right, let's take a look at the elastic collision example. So this is a specific type that has two conditions. One, kinetic energy also has to be conserved, and momentum has to be conserved. So when I talk about kinetic energy being conserved, that means there's no change in the kinetic energy of the two objects before or after. So let's go ahead and read this problem and then solve it. So here we are. On a cold winter day, a penny, mass 2.5 grams, and a nickel, mass 5 grams, are lying on a smooth, frictionless surface of a frozen lake. With your finger, you flick the penny toward the nickel with a speed of 2.2 meters per second. The coins collide elastically. Calculate both their final velocities, speed and direction. So the elastic is telling us those two conditions are being met. So I'm going to list out my information here. So I have my penny, it's moving in at 2.2 meters per second. I'm going to call to the right my positive direction. And whenever I do that, I go ahead and I just make a note that this is my positive direction, this is my negative direction. So I see that this is a positive 2.2 meters per second. And the nickel is initially stopped. After the collision, they are moving. Now, they are in grams, so we will have to convert those to kilograms, but I have a tricky tiger trail for us here. So our tricky tiger trail is that this mass is twice this mass. So what I could do is I could call this mass 2m1. So what is the benefit for us there? Well, when I come over to my conservation momentum equation and I cross out those zeros, so initially the velocity is 0 for m2, and I make this substitution of 2m1, what happens is I have m1 v1 equals m1 v1 prime plus 2m1 v2 prime. And so now in making that, I have an m1 in every term, so it cancels out. So it just makes my math a little bit easier if there is a ratio like that. If not, you just have to keep those masses in there. Okay. And I can do the same thing over here in my kinetic energy. So I cross out any term that is going to be 0, so the initial velocity of 2 is 0. This equation for kinetic energy is on your equation sheet. It just says delta K equals this, but in this case, remember delta K is 0 in these elastic collisions, so I just put a 0 there. All right. Because it is 0, and don't make this mistake when finding kinetic energy, because it's 0, all the terms have a 1/2. I can cancel out those 1/2s. And so my next step is I got m1 v1 prime squared plus m2, but instead of m2 here, we're going to write 2m1 using that tricky tiger trail, v2 prime squared minus m1 v1 squared. And remember, if you have two terms here, make sure you distribute that negative sign or keep that parenthesis, equals 0. So just like the 1/2s cancel because there was 1 in every term, my m1s are going to cancel for me here. And so now I have two equations, two unknowns. And that is kind of the tricky part of these elastic ones, is I'm going to have two unknowns that I need to solve for, and they're not the same like is in a recoil or maybe in perfectly inelastic. So how we solve this is we're always going to solve this momentum equation first, because that makes it a little easier for us, because then we can substitute into this kinetic energy equation and we won't end up with any square roots. But we will end up with something that's kind of ugly, namely a quadratic. And so because I end up with a quadratic, we're going to go ahead and just use solver since it's already set equal to 0, as opposed to turning it into a polynomial and using polysimult. So let's go ahead and do that. So we're going to solve for one of our unknowns. So maybe I'll solve for v2 here. So I have v1 minus v1 prime all divided by 2 equals v2 prime. And I'm just going to go ahead and substitute this in over there. So now I have 0 is equal to v1 prime squared plus 2 times, substitute in, v1 minus v1 prime divided by 2 quantity squared minus v1 squared. Now I know what v1 is, it's 2.2. I just don't know what v1 prime is. So just have to kind of go ahead and figure this out. So I'm going to plug in my numbers. So I have 2.2 squared. Oops, I'm sorry, that's my unknown one. V1 prime squared plus 2 times 2.2 minus V1 prime all divided by 2, quantity squared minus 2.2 squared. So I'm going to go ahead and type this into Solver. And when I type this into Solver, it's going to tell me what V1 prime is. Now the problem with Solver is you got to give it the guess, remember? And so what we're going to do is we're going to go look at the air track in the back and kind of get an idea of, well, when one object comes in and hits a stationary object in an elastic collision, what can I kind of predict about that final velocity? So let's go to that air track. All right, so we have the air track here, and we're going to look at what happens when we run different size objects into each other, and specifically when the object being hit is stationary. So the first one we're going to do is we're going to run a equal into an equal. So these have equal mass. The reason we're using the air track is it removes friction from our problem. So we can talk about conservation of momentum. So we're going to have one station where we're going to run one of these into the other one and see what happens. Then we're going to take this one, which has this little mass on top, and we're going to run a small one into the big one and the big one into the small one. We're going to see what are those final velocities of the incoming object going to be. All right, so this will be a little bit noisy, but we'll do what we can to work that out. So let's turn this on here. And again, this air track just works like an air hockey table. The difference is it's kind of bent, and then these little carts sit on top of it, and they just kind of hover on that air. All right, so we're bringing in the little one into a stationary little one. We'll let it settle down there. And we'll see that when that one hits, it comes to a stop. All right, so as it comes in, equal masses, the incoming one stops. Now when I bring in the larger one, when the larger one comes in, we see that it continues on a little bit. Okay, so when that larger one comes on, it continues on in the direction it was moving. It had more momentum, and so it continues on. Now if I bring the little one into the big one, we'll see that it bounces back. Okay, so the reason we want to look at that is because this will allow us to estimate which type of direction the final velocity is going to be for that incoming one. All right, so we saw in the air track that if I send in a smaller mass, it should bounce backwards. So I should be getting a negative number for V1 prime here. And the two solutions that you're always going to get for these are the solution that nothing happened. They didn't actually collide because momentum and energy would be conserved. So I would get a V1 prime of 2.2 and a V2 prime of 0. That's not the solution we want. We want the one that's negative. And so I put in a negative value, and I got a negative 0.73 here. So I got V1 prime is negative 0.733 meters per second. Go ahead, plug that number back in over here to find V2 prime. And V2 prime, I got a positive 1.47 meters per second. Now, what does these positives and negatives mean? The negative, I would write this as 0.733 meters per second opposite the original direction of the penny, and I would say this is 1.47 meters per second in the original direction of the penny.